इसका रिस्पॉन्स शीट होगा, टाइलिंग जिस पे लिखा होगा, आप सभी के बैग में रिस्पॉन्स शीट होगा, वो निकाल के आप उसके अंदर जो क्वेश्चंस हैं, जो प्रश्न पूछे गए हैं, उनके जवाब लिखने की कोशिश कीजिए जिस भी भाषा में. इफ यू वांट यू कैन राइट इन इंग्लिश, इफ यू वांट यू कैन राइट इन.
Yeah, see, either you saw that this is about maths, but there is no numbers. Okay, some or other we have this assumption, mathematics means number and manipulating number. Bigger the number it is bigger mathematics. No, mathematics is about pattern. It's about exploring patterns. I mean, one aspect of mathematics is about exploring patterns, and the patterns can be things like this styling. Okay, so it can be things like this styling, and many of the things that we talked here have use and application in various aspects of our life. For example, how the protein folds. Here we have talked only about the two-dimensional tiling, symmetry. But if you are looking at how protein fold, I mean, it's a three-dimensional one. There is huge amount of this mathematics in that. So, how many ways it can fold, how many ways it can make an arrangement, makes different kinds of effect. I mean, so you use quite a lot of this in, for example, today in biochemistry, molecular biology, you use quite a lot of this mathematics. Even in frontier areas of physics called M theory, or popularly called as string theory, you use this kind of mathematics. Okay, so you don't actually look at numbers, because numbers don't matter. I think we should go to the next episode. Okay. Then that will also be right.
Next, ये जो आपने अभी देखी टाइलिंग, कि कैसे हम किसी शेप को जोड़ करके टाइल का जगह बिल्कुल बीच में गैप रखे बिना जोड़ करके बना सकते हैं, और क्यों कुछ शेप इस तरह का काम करती हैं कि उनके बीच में गैप नहीं है, और क्यों कुछ शेप्स ऐसी हैं जिनके बीच में गैप आ जाता है. और आपने देखा सारे विश्व में कैसे कैसे लोग हैं जिन्होंने टाइलिंग के अंदर किस किस तरह के प्रयोग किए. खासतौर से MC एस्चर, जिन लोग बच्चों के पास इंटरनेट का है वो MC एस्चर का नाम डालें तो बहुत सुंदर सुंदर पैटर्न आपको आएंगे, और आपको अचंभा होगा कि उन्होंने क्या क्या काम इस सबसे किए.
Our world is populated with numerals, but we rarely stop to think about them. Where did they originate? How did they evolve? Well, the answer is the numbers we use today evolved in India. And the story of how they moved across the world is a fascinating one. To this episode of The Maths Factor, where we're going to explore the intricacies of our number system. We will become world travelers to see how numbers have evolved in different systems. We're also going to show you how both animals and babies can understand numbers intuitively. So gear up as we kickstart our journey right away. As civilization started to develop across the world, there surfaced the need for notation and for numerals, the need for keeping records. But before we start tracking these developments, let's see if you know the difference between numbers and numerals. Well, it's quite simple. The number is the idea, the numeral is the notation. The first stop on our journey is South America in the 1400s, the land of the Incas. This is Machu Picchu, the famous Inca site that lay forgotten for centuries. This urban creation is a testament to how advanced the Incas were as a civilization. They had roads, textiles, cities, agriculture, and government. Now, curiously, they seem to have had no written language. Now, when the Spanish conquistadors landed in South America in 1532 CE, they found no sign of written numeral records. What they did find, huge amount of knotted ropes, like this. These were no normal ropes. In fact, they were called quippers. They were a way of recording information that were unique to this region. Shall we try our hand at making a quipper? Rinaldia is an eccentric lawyer who's going to try and categorize the books in a library using a quipper. She needs to separate her journals, case books, and fiction. She first takes strings of many different colors and then starts by tying knots in them. She has 121 journals, so the first rope, which is yellow, she makes 1, then 2, then 1 knot, like this, which means 121. She uses a red string to show she has 31 case books, and an orange string to know she has 12 fiction books. And the last strand, which is green, is used to tally them all up, 264. Renard has made a quippo that effectively categorizes her library. Real quippos were much more complex than this. Some had hundreds of strings, and extra strings tied to ones hanging from the base. It is important to remember that the quippo is not a calculating device. It is just a way to store numbers. There were even special people who were in charge of deciphering the quippo, called Kipukamayaks, or keeper of the quippo. Okay, from South America we move to ancient Egypt and Babylon. First to Egypt, all the way back in 3000 BC. When we look at the pyramids and the temples constructed at that time, it is clear that a degree of mathematical sophistication was needed to build these. Some of our most important understanding of the mathematics of ancient Egypt comes from two papyruses known as the Rhind Papyrus and Moscow Papyrus. These were not treatises, but broadly lists of practical problems which were used to train people in mathematics. The Rhind Papyrus contains 87 problems, while the Moscow Papyrus contains 25. The Egyptian numeral system is visible both in artworks from the time and in monuments. From these it is clear that they used maths in agriculture, surveying, and trading. Let's take a quick look at how their numbers work. The Egyptians used hieroglyphics or pictorial signs to denote numbers. They had a special system for every power of 10, which looked a bit like this. This was 1, 10, 100, 1,000, 10,000, 100,000, 1 million. So they could write numbers all the way to 1 million. They used to use repetition to write a number. So 4,622 would look like this. Now the problem arose because they did not have a place system. Wondering why that was a problem? Well, writing 1 million was simple, but writing 99,999 required 45 symbols. Let's move from Egypt to ancient Babylon, where numerals were developed about 5,000 years ago. Unlike the Egyptians, who counted in groups of 10, the Babylonians counted in groups of 60. So how did the numerals work? Any number less than 10 had a wedge that pointed down, so 4 would look like this. The number 10 was symbolized by a wedge pointing to the left, so 20 would be. Numbers less than 60 were made by combining the symbols of 1 and 10, so 47 would look like this. And from 60, they would start all over again. So this is what 64 would be like. So they didn't have a symbol for 0, but they did use the idea of 0. When they wanted to express 0, they just left a blank space in the number they were writing. So if it is 60, there would be a single wedge mark and a dash. When they wrote 120, they would put 2 wedge marks and a little dash in the second place. The Babylonian calendar worked in the unit of 60. Year had 360 days. Each day was divided into 24 hours, each hour into 60 minutes, and each minute to 60 seconds. And this form of counting has survived for 4,000 years. We've been traveling across the ancient world to see different forms of numerals. We could keep going. The Mayans, the Greeks, and the ancient Romans developed their own unique counting systems. We've dropped the Mayan and the Greek ways, but we still use Roman numbers today, for clocks, to denote centuries, to suffix the names of kings and tombstones, etc. Let's now see how numbers come naturally to most of us. Even animals. Take a bird. She has a nest with 4 eggs. If you take 1 out, she may not notice, but when you take 2 out, she will desert the nest, because she has realized that there is a predator somewhere close. This means she can tell between 2 and 3. Sounds random? Well, let me share a more documented experiment done on bees by a group of scientists from the Vision Center in Australia. The scientists showed the bees a number. So if it was 3, there would be 3 dots. Then they flew on into another chamber. Here they were faced with 2 forks, one with 3 and the other with some other number, say 4 dots. Now, if the bee picked the same number, in this case 3, the scientists added an incentive. They got a hidden sugar solution as a reward at the end of the fork. If they chose the wrong pattern, they were released and allowed to try again. And the bees did pretty well. They were more often than not chose the same pattern that they had seen earlier. To show that they were recognizing numbers and not just shapes, the scientists would vary the representation of the number. So they would first show the bees 3 dots, and then the next fork would have 3 stars. By the end of the experiment, the scientists were able to conclude that the bees could count till 2, 3, and sometimes till 4. Similar experiments have been done with chicks, pigeons, and monkeys, to name a few. And from this, we are able to conclude that animals are able to discriminate between small numbers. What about babies? And I mean tiny ones who haven't started walking or talking and clearly haven't been taught numbers. Let's look at an experiment done by